Certainly, I have to thank team and ABB for this kind invitation to Orlando. It's a pleasure being here, beautiful country, first time in Florida. I'm afraid I'm too old to visit Disneyland, but in any case, I appreciate the atmosphere. As you can see, I am from Pisa. Pisa is well known for a great mistake made a few centuries ago by a local architect. The final result is a tower which actually was used by Galileo Galilei to perform a few experiments, just throwing spheres from the tower and see if the heaviest sphere was arriving before the lighter one. And everybody knows the answer. After Galileo, also Enrico Fermi was a student of my university, and this explains probably why in Pisa physics is a very good department, still even now. Chemical engineering is not as good. I've been working there since mid-70s, which is a lot of time. And I've been working in multi-phase flow. When you work in an applied sector, at a certain point you realize that what you are finding can be used by the industry. And being an engineer, that was interesting enough to go on in this direction. Tea Sistemi is now a company with more than 50 people. We have been working with a number of companies around the world. ABB is one, but Eni, the Italian oil company, is another one. We, being a small company, we have a big lab. In our lab, we can make experiments at the same actual field conditions, which is rather unique for a small company. Big oil companies have these labs. Norwegians have these labs, but this is quite obvious. They have everything, even the oil. Among the experiments and the new technologies of which I'm proud, in the last 3-4 years we've been working to this project named CUBE, Containment of Underwater Blowout Events, and this has been a joint activity with Eni. I'm proud because just 3 months ago we had the first open sea test of the system and it works. And it is actually a subsea gas liquid separator. But let's go to the business. The business today is multi-phase metering. Well, somehow team reported this data. Apparently, we have more than 5,000 multi-phase flow meters installed all over the world by now. And this is a very small percentage of the total number of wells, which means that this business must grow. But of course, there are a couple of questions. Is it going to continue this growth rate with the barrel at $30? And should we look for cheap equipment? You know, we have been spoiled probably by the high oil cost in the last, say, 10, 20 years. A number of technologies have been and became probably more complex and more expensive than they should. So the question is, can we do the same job, eventually possibly better, at a lower cost? And I will try to answer to this question. By the way, the reference is on the bottom of the slide, and of course it's very optimistic in its title. But everybody, I suppose, hopes that things will improve. Now, what is called multi-phase flow meter actually is a combination of different instruments. And this instrument, none of these instruments does direct measurements of the flow rates. Measurements are indirect. Eventually, you may measure the water cut, but not the water flow rate. You may measure the momentum of the mixture, but not single-phase flow rates. In order to get the flow rates, you use empirical equations. And the error of the instrument and the error of the equations makes these meters not very reliable. And one may ask, why we use an instrument when we know that it is not reliable? And the answer is a kind of axiom or theorem, which essentially tells you that, okay, if you can check if the instrument works, you check and you use this data to calibrate your instrument. If you cannot check, by definition, the system is working fine, because nobody can show that it's not the case. Now, in the last years, everybody started to ask for independent verification in independent labs and stuff like that. But again, these instruments are still not very accurate, even if they are improving, because you build up the system also with the experience. There are meters or systems which do not need hardware. You can just use all the signals which you receive in order to, especially pressure signals, in order to deduce the flow rates. And these systems are quite used, and we have had, as a company, a number of experiences which I will show you something about. And finally, there are other instruments. I will not go too much into this, because this now is a commercial instrument which obtains the flow rates by a sampling method. And I will tell something about this, but in this case, the measurement is direct. You don't need calibration, you don't need empirical closure equations. But today I'm not going to talk about this. I much more will talk about the first method, which essentially is a low-cost method and can be very, very smart. I will tell something about what we have been done in our company in the last 25 years. Like everybody else, we started with the gamma densitometer, the Venturi, and the impedance meter. Everybody started this way in this business. But then we quite early went in other directions, mainly because the competition was too strong, and my background is not in the instrumentation. My background is in fluid dynamics, and my competitors at that time were much better than me in developing fancy instruments, also good-looking instruments. We went into the business of virtual flow meters. So what can you get from pressure signals? A couple of examples are this beautiful work we have been doing for Well Dynamics, which is a company building smart well completions. And they have measurement of pressure downhole at different levels. And we were testing the system and trying to obtain the flow rates from the pressure signals. And we were successful. At least people in Well Dynamics were very happy. They used the system for a while. Then probably they went by their own when they were bought by Halliburton. I don't know the story yet. Another example, which is much more recent, is an entire platform, Dipanuke, which is quite north with respect to here, And the entire platform provides information about what is arriving and what is leaving the platform. And the analysis of these signals, especially pressure signals through the valves, gave us the production rates. And this work is still going on. We are going every while to Deep Panuke to tune up the system to obtain more data to correct possible errors. The final business we entered in is the wet gas case. The wet gas case is a special case because wet gas is particularly tough for everybody. Companies which are selling multi-phase flow meters tend to use gamma densitometers also to say detect the liquid or the liquid holdup in wet gas. This is possible, of course, but you need to have enough liquid. And if the liquid is not enough, you are not going to have good information about the liquid production. And sometimes you use that flow meter just to know how much liquid are you producing. So the meter is useless if it is not able to provide you with a good number about the water production, for instance. So we started to use a different method, isokinetic sampling. I will tell you about this method in the following slides. But what is interesting is that with this technique, in the first application we've done here in the Gulf of Mexico almost 15 years ago, we have been able to read with very good accuracy 0.2% of liquid and 0.02% of water. And then we had a mission impossible to measure 2 multiplied 10 to the minus 5% of liquid, and we were successful. You know, with the sampling method, it's only a matter of being good enough in the sampling business, and you can measure extremely low liquid flow rates. So low that nobody believes it. If I put out this figure, nobody in the audience will believe that I am able to measure such a small liquid fraction. Nobody believes, but it is true. And this is the system. You know, isokinetic sampling means that I have an orifice, I measure the pressure differential in an orifice without sampling. Then I make sampling 10% through a special section of the pipe, and my pressure drops decrease to 81%. And in this case, I know that I'm sampling 10%. So the concept is extremely simple. Of course, it has been patented, but it's very simple. You know, you only need a pressure differential, and you set the sampling at the level that you get, say, if you want to sample 10%, you have to set the system with pressure drops, ratio of pressure drops to 81%. So this is a very simple concept. You can see how do we measure then the liquid. We take a small sample. So we measure the liquid flow rate from the time required to fill a given volume of pipe, which is also extremely accurate. Even if you have a very small liquid flow rates, you can measure very well small liquid flow rates because you take the time needed. Then, of course, you can make also the liquid-liquid separation, which means that I can measure not only the fraction of water, but eventually the flow rate of water, because I can see what is the rate of accumulation of water in my system. So, by definition, this sampling method can be extremely simple, even with extremely small liquid flow rates. And probably the oil industry is not yet used to the idea that it is possible to measure such low liquid flow rates, but it is possible. The The first industrial application has been made almost 15 years ago and was a big challenge because it was, a platform in the Gulf of Mexico. The production was, for us, enormous, up to 100 million standard cubic feet per day, with very small water, very small condensate. And of course, there was methanol over there because the problem was avoid hydrate formation. So from the platform, they wanted to know how much water they were producing in order to inject the right amount of methanol. So everything was clear. In this case, we have been able to determine, with comparison with, say, a well testing separator. No, it was not a well testing, it was a real physical metering system. The error in the liquid flow rate was below 2%. The error in the water flow rate was a little bit higher, but again, very, very small. So this is isokinetic sampling. I told you about isokinetic sampling because I'm going to go back to this topic. Last year, when, as I think everybody, we start feeling the problem of low cost of the oil, we started to think if we could develop a low-cost flow meter. So the idea is, let's go back to the virtual flow metering, which is so very simple. But, a pure virtual flow meter does not provide all the information which is required. So we ended up with something which is similar, but not exactly the same. We just said, why don't we have a simple pipe, and we can measure, say, the static head, which is the component of the pressure gradient, vertical pressure gradient due to gravity, which is immediately correlated to the liquid holdup. And then we use an orifice, which is a simple device. It's an obstruction. It's like a valve at the end. This system, of course, is very intelligent because we want to replace with a pressure transmitter, and probably ABB are so happy with me because this idea probably, they may like it. We replace a gamma densitometer with a differential pressure transmitter. The point is to analyze the data, but you have exactly the same problem with the gamma densitometer. The gamma densitometer does not give you the liquid fraction, gives you the liquid holdup. It's different, it's very different. In order to derive the liquid fraction, which is the volume liquid fraction in the system, from the liquid holdup, you have to go through modeling, and these models quite often fail. You need, in our case, good experiments in order to find the correlations. If we watch to what we get from the lab, we get this mess of data. These data are taken with the real final equipment. Changing the liquid viscosity is only gas liquid viscosity, gas density, and of course the flow rates. And you get all this mess of data. If you watch the data more carefully and you think that you have, say, pressure losses which are gravitational and frictional terms, and you model the two terms, and you express the two terms in with a number, a big number of dimensionless numbers, and then you find a beautiful fit. The same you can do with the orifice. You do the same process. You make the experiment. You take the data in the lab at actual field conditions. Of course, there is a little discussion here. Why an orifice and not a Venturi meter? It is a matter, again, of, in this case, of culture. If I want to measure with good accuracy single-phase flow rate, I may prefer a Venturi meter. But when dealing with multi-phase flow, there is no advantage in using a Venturi meter. It is only more expensive. but you do not recover pressure. You have the same problems in correlations and in analyzing its data. So it doesn't make any sense using a Venturi. An orifice is nothing, and you can change the orifice very easily. So if you go the same mass of data, you find all the effect of gas density, liquid viscosity, then you find the correlation, the same dimensionless numbers, and you find a fairly good correlation. When you combine the two correlations in order to predict the liquid and gas flow rate, you get an error of 2% in the liquid, 4% in the gas. Of course, this is everything under control, everything is perfect, but error of 2% is within the error of the experimental measurement, so it is almost exact. So this demonstrates that I can measure liquid and gas flow rate easily with a very, very simple system, cost zero. But what about the water cut? The water cut usually is a mess, but it is a mess for everybody. If they tell you we measure the water cut, I personally, having done personally this experience, I don't believe. Because you need the salinity of the solution, and you need to know which is, you may switch from one continuous phase to the other continuous phase. There may be conditions where it is really difficult to measure this. So what we do is we started from here, we put a small sampling section, and we do exactly the same job you have seen before. The cost of this section is the cost of 2-3 multi-phase differential pressure measurements. So we measure the water and the oil fraction just by sampling, and that's it. We are done. What means, after all this presentation, intelligent? We used all the data. We tried to determine the flow patterns. We had a very fundamental approach in order to understand what could be the correct modeling system. And there is also a little trick. We have a redundant measurement because we can measure the liquid flow rate also knowing the sampling flow rate, because we have verified in the lab that this ratio is constant for a wide range of parameters. And of course, in this case, intelligent means also low cost. That's the conclusions. Main points I've been going through is that a single differential pressure measurement can replace a gamma densitometer, and nobody likes a gamma densitometer. The second point is that the quality could eventually deteriorate, but in any case, you need to do modeling. In any case, you have to make your efforts in order to derive from your data the information which you need. So it is a matter of using well your data, of exploiting your data to the maximum. This flow meter probably costs 1/3 than the competitors in general. We don't have radioactive sources. It is very simple. Eventually, you don't need even to construct it. You can use what you have and add the sampling system. There is a final question, of course. If it is better to invest your money, and I'm talking about, for instance, oil companies, in developing instruments or in developing knowledge. And of course, being at the end also a university professor, I rather prefer the last choice. Thank you.